Dynamics. Exercises pages 107 to 108. Exercises Q1.1, page 107. Choose the correct option. A gas in a closed container is heated with 10 J of energy, causing the lid of the container to rise 2 meters with 3 N of force. What is the total change in energy of the system? 1. 10 J2. 4. J3. 10 J4. 4. J. Solution. 4J. Explanation. For this problem, use the first law of thermodynamics. The change in energy equals the increase in heat energy minus the work done. Delta U equals Q, W. We are not given a value for work, but we can solve for it using the force and distance. Work is the product of force and displacement. W equals F delta X. W equals 3N times 2 meters. W equals 6J. Now that we have the value of work done and the value for heat added, we can solve for the total change in energy. Delta U equals Q, W. Delta U equals 10J 6J. Delta U equals 4J. Exercises Q1.2, page 107. Choose the correct option. Which of the following is an example of the first law of thermodynamics? 1. The specific heat of an object explains how easily it changes temperatures. 2. While melting, an ice cube remains at the same temperature. 3. When a refrigerator is unplugged, everything inside of it returns to room temperature after some time. 4. After falling down the hill, a ball's kinetic energy plus heat energy equals The initial potential energy. Solution. While melting, an ice cube remains at the same temperature. Exercises Q1.3, page 107. Choose the correct option. Efficiency of a Carnot engine is large when ATH is large, BTC is low, CTH, TC is large, DTH, TC is small. Solution. Exercises Q1.4, page 107. Choose the correct option. The second law of thermodynamics deals with transfer of A. Work done, B. Energy, C. Momentum, D. Heat. Solution. B. Energy. D. Heat. Exercises Q1.5, page 107. Choose the correct option. During refrigeration cycle, heat is rejected by the refrigerant in the 1. Condenser 2. Cold chamber 3. Evaporator 4. Hot chamber. Solution. Condenser. Exercises Q2.1, page 107. Answer in brief. A gas contained in a cylinder surrounded by a thick layer of insulating material is quickly compressed. Has there been a transfer of heat? Solution. No, there is no transfer of heat energy, as the cylindrical vessel is surrounded by an insulating material, which doesn't allow heat transfer. Exercises Q2.2, page 107. Answer in brief. Give an example of some familiar process in which no heat is added to or removed from a system, but the temperature of the system changes. Solution. Adiabatic compression is the process in which no heat is transferred to or from the system but the temperature of the system changes. When we compress gas in an adiabatic process, the volume of the gas will decrease and the temperature of the gas rises as it is compressed, which we have seen the warming of a bicycle pump. Conversely, the temperature falls when the gas expands but the heat remains constant throughout the process. Exercises Q2.3, page 107. Give an example of some familiar process in which heat is added to an object, without changing its temperature. Solution. I. Melting of ice, E. Boiling of water. Exercises Q2.4, page 107. Answer in brief. What sets the limits on the efficiency of a heat engine? Solution. The temperature of the cold reservoir sets the limit on the efficiency of a heat engine. This formula shows that for maximum efficiency, Tc should be as low as possible and Th should be as high as possible. Exercises Q2.5, page 107. Answer in brief. Why should a Carnot cycle have two isothermal, two adiabatic processes? Solution. With 2 isothermal and 2 adiabatic processes, all reversible, the efficiency of the Carnot engine depends only on the temperatures of the hot and cold reservoirs. Note: this is not so in the Otto cycle and diesel cycle. Exercises Q3.1, page 107. A mixture of hydrogen and oxygen is enclosed in a rigid insulating cylinder. It is ignited by a spark. The temperature and pressure both increase considerably. Assume that the energy supplied by the spark is negligible. What conclusions may be drawn by application of the first law of thermodynamics? Solution: the internal energy of a system is the sum of potential energy and kinetic energy of all the constituents of the system. In the example stated above, the conversion of potential energy into kinetic energy is responsible for a considerable rise in pressure and temperature of the mixture of hydrogen and oxygen ignited by the spark. Exercises Q3.2, page 107. A resistor held in running water carries electric current. Treat the resistor as the system. A. Does heat flow into the resistor? B. Is there a flow of heat into the water? C. Is any work done? D. Assuming the state of resistance to remain unchanged, apply the first law of thermodynamics to this process. Solution: A. Heat is generated into the resistor due to the passage of electric current. In the usual notation, heat generated equals I2RT. B. Yes. Water receives heat from the resistor. C. L2RT equals mc delta T plus P delta V Q delta U W. Here, I equals current through the resistor, R equals resistance of the resistor, T equals time for which the current is passed through the resistor, M equals mass of the water, S equals specific heat of water, T equals rise in the temperature of water, P equals pressure against which the work is done E by the water, delta U equals increase in the volume of the water. Exercises Q3.3, page 107. A mixture of fuel and oxygen is burned in a constant volume chamber surrounded by a water bath. It was noticed that the temperature of water is increased during the process. Treating the mixture of fuel and oxygen as the system, A. Has heat been transferred? B. Has work been done? C. What is the sign of increment U? Solution: A. Heat has been transferred from the chamber to the water bath. B. No work is done by the system, the mixture of fuel and oxygen, as there is no change in its volume. C. There is an increase in the temperature of the water. Therefore, delta U is positive for water. For the system, the mixture of fuel and oxygen, delta U is negative. Exercises Q3.4, page 107. Draw a PV diagram and explain the concept of positive and negative work. Give one example each. Solution: consider some quantity of an ideal gas enclosed in a cylinder fitted with a movable, massless, and frictionless piston. Expansion of a gas. Suppose the gas is allowed to expand by moving the piston outward extremely slowly. There is a decrease in the pressure of the gas as the volume of the gas increases. The figure shows the corresponding PV diagram. Positive work with varying pressure. In this case, the work done by the gas on its surroundings. Negative work with varying pressure. The figure shows the corresponding PV diagram. Exercises Q3.5, page 107. Answer in brief. A solar cooker and a pressure cooker both are used to cook food. Treating them as thermodynamic systems, discuss the similarities and differences between them. Solution: solar cooker. Solar cooker was invented by Horace Benedict de Saussure in 1767. Solar cooker is a device used to cook food by using no fuel, instead of sunlight. Solar cookers use a parabolic reflector to collect the rays of the sun and focus them at the cooker to heat it and cook the food in the cooker. Today the solar cookers are a little bit expensive than pressure cookers. Big solar cookers can be used to make food for people on a larger scale. Pressure cooker. Pressure cooker was invented by Denis Papin. Pressure cookers are the most common cookers used in our houses and can be found in every house. Pressure cookers require water to convert it into steam for raising the internal temperature and pressure that permits quick cooking. Pressure cooker are cheaper than solar cookers. Pressure cookers requires a fuel for heating the liquid inside them. Exercises Q4, page 108. A gas contained in a cylinder fitted with a frictionless piston expands against a constant external pressure of 1 atmosphere from a volume of 5 liters to a volume of 10 liters. In doing so, it absorbs 400 J of thermal energy from its surroundings. Determine the change in the internal energy of the system. Solution. Data. P equals 1 atmosphere equals 1.013 by 105 pascals. V1 equals 5 liters equals 5 x 10 to 3 m3. V2 equals 10 liters equals 10 x 10 to 3 m3. Q equals 400 J. The work done by the system gas in this case on its surroundings. W equals P, V2 V1. Equals 1.013 by 105 pascals, 10 x 10 to 3 m3 to 5 x 10 to 3 m3. Equals 1.013, 5 x 102 J. Equals 5.065 x 102 J. The change in the internal energy of the system. Delta U equals Q. W equals 400 J 506.5 J equals 106.5 J. The minus sign shows that there is a decrease in the internal energy of the system. Exercises Q5, page 108. A system releases 125 kilojoules of heat while 104 kilojoules of work is done on the system. Calculate the change in internal energy. Solution. Data. Q equals minus 125 kilojoules, W equals 104 kilojoules. Delta U equals Q. W equals minus 125 kilojoules minus 104 kilojoules. Equals minus 125 plus 104 kJ equals 21 kilojoules. This is the change decrease in the internal energy. Exercises Q6, page 108. The efficiency of a Carnot cycle is 75%. If the temperature of the hot reservoir is 727 degrees Celsius, calculate the temperature of the cold reservoir. Solution. Exercises Q7, page 108. A Carnot refrigerator operates between 250 degrees K and 300 degrees K. Calculate its coefficient of performance. Solution. Exercises Q8, page 108. An ideal gas is taken through an isothermal process. If it does 2000 J of work on its environment, how much heat is added to it? Solution. Data. W equals 2000 J, isothermal process. In this case, the change in the internal energy of the gas, delta U, is 0 as the gas is taken through an isothermal process. Hence, the heat added to it. Q equals delta U plus W equals O plus W equals 2000 J. Exercises Q9, page 108. An ideal monatomic gas is adiabatically compressed so that its final temperature is twice its initial temperature. What is the ratio of the final pressure to its initial pressure? Solution. Exercises Q10, page 108. A hypothetical thermodynamic cycle is shown in the figure. Calculate the work done in 25 cycles. Solution. Exercises Q11, page 108. The figure shows the VT diagram for one cycle of a hypothetical heat engine which uses the ideal gas. Draw A the PV diagram and B PT diagram of the system. Solution. Exercises Q12, page 108. A system is taken to its final state from initial state in hypothetical paths as shown. Figure. Calculate the work done in each case. Solution. Data. PA equals PB equals 6 by 105 pascals, PC equals PD equals 2 by 105 pascals. VA equals VD equals 2L, VB equals VC equals 6L, 1L equals 10 minus 3 meters 3. The work D1 along the path A right pointing arrow B, isobaric process WAB equals PA, VB, VA equals 6 by 105 pascals, 6 to 2 10 minus 3 meters 3 equals 2.4 x 103 J. EWBC equals 0 is the process is isochoric, V equals constant. The work done along the path C right pointing arrow D, isobaric process WCD equals PC, VDBC equals 2 by 105 pascals, 2 to 6 10 minus 3 meters 3 equals 8 x 102 J. IVWDA equals 0 is V equals constant.